Good evening, dear student. Today I am going to discuss DRF block chapter. So this chapter belongs to your class 12 syllabus, and this one also belongs to your inorganic syllabus. So I am Rahul Devnath. So I hope all of you watch my previous videos, which are already uploaded in my channel. So I hope all of you subscribe and share my channel. So I am also request to you, please watch my videos and subscribe, like and share my videos. Also you will get benefit from my videos. Okay. सो आज हम लोग DRF ब्लॉक की चैप्टर डिस्कस करने वाला हूँ, ठीक है. सो DRF ब्लॉक दिस चैप्टर इज इनऑर्गेनिक चैप्टर, इज इम्पोर्टेंट चैप्टर. बोर्ड में 3-4 मार्क तो मिल जाएगा, प्लस एंट्रेंस में 2 क्वेश्चन मिल जाएगा इसके ऊपर. नीट में जीमेन में भी मिल सकते हैं, कभी भी मिलता है कभी नहीं भी मिलता है. एंड दिस चैप्टर इज द बेसिक चैप्टर फॉर कोऑर्डिनेशन केमिस्ट्री. ओके. सो DRF block, that is D block element and F block element. Okay. So D block elements and F block elements is known as transition element. What? This is known as transition element. Transition element. Okay. D block is known as outer transition element. This one is known as inner transition element. F block is known as inner transition element. Clear, people? So D block element have normal general configuration. This configuration is n-1 whole to the D 1 to 10 ns 0 to 2. This is the general configuration of D block element. It's very important. आपके कभी कभी बोर्ड में भी मिल सकते हैं. और F block element के लिए और एक configuration है n-2 f 1 to 14 n-1 d 0 to 10 ns 1 to 2. Clear, people? This is the general configuration of D block element, and this one is the general configuration of F block elements. This one is F block, this one is D block. कभी भी पूछ सकते हैं, आपके बोर्ड एग्जाम में मिलेगा, मे बी इससे पहले भी आ चुका है इसके ऊपर क्वेश्चन, जनरल कॉन्फ़िगरेशन के ऊपर क्वेश्चन. सो another things, what is transition element? What is the definition of transition element? Clear? Transition elements are those elements which are not completely filled. They are D and D orbital, that is D orbital, not F. For F block, that is F orbital. Clear? So D1 to D9 configuration is known as transition element. Clear, people? D1 to D9 configuration is known as transition element. For example, first row transition element, first row is scandium to copper and zinc. So copper is known as transition element, but the zinc does not. Why? Actually, if you write its configuration 1s2, 2s2, its atomic number is 21. Then 3s2, 3p6, 4s2, 3d1. This is the D1. So D1 to D9 configuration is known as transition element. But if you consider zinc, if you draw its configuration 1s2, this is 30. What? 30. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. That is 10 is completely filled. That's why this one does not consider as a transition element. Clear, people? Transition element means are those elements which has not completely filled. They are D orbital. That is D1 to D9 configuration elements is known as transition element. Similarly, also F block elements F1 to F9 configuration is known as transition element for F block series. Clear, people? Okay, next, in D block elements also known as what? Outer transition element. D block element is known as outer transition element. Why? Actually, what happened in D block elements? These are also called transition element, outer transition element. Actually, डी ऑर्बिटल में क्या होता है, हर कोई एलिमेंट की सेंटर में क्या होता है, न्यूक्लियर होता है और साइड में ऑर्बिट होता है। डी ब्लॉक में ऑर्बिट, डी ऑर्बिटल थोड़ा आउटर साइड में होता है, और एफ ब्लॉक में क्या होता है, दिस ऑर्बिटल प्रेजेंट इन इनर साइड। क्लियर पीपल, दिस इज प्रेजेंट इन inner side, that's why it is known as inner transition element, this one is known as outer transition element. Due to the outer transition element, their interaction force is less because distance is maximum between the orbital and nuclei, whereas in a block series this distance is less, so interaction force is more. Clear? So that's why d block transition element require less ionization potential. This one require less ionization enthalpy. Clear? But this one require more ionization enthalpy. Clear people? Pakka. So that's why d block element shows variable oxygen state from +1 to +7, but in a block element shows +1 to +4. Clear people? So this shows maximum number of oxygen state, and +7 shows manganese. Manganese shows +7 oxygen state. Clear people? This is very important point. ये बहुत बार आपके एग्जाम में मिल सके, ऑलरेडी आ चुका है. Among them which element shows maximum number of oxygen state, that is manganese. This one shows +7 oxygen state. Clear people? So in d block series, first row transition element, second row transition element, and third row transition element are divided basically three categories. This one is first row, second row, and third row. First row is scandium to zinc. Second row, that is yttrium to cadmium. Third row is hafnium to mercury. Clear people? This is the first row, start from scandium and end in zinc. Clear people? This is the first row transition, this one is second row, this one is third row. So, but zinc, cadmium and mercury does not consider as a transition element. This is not consider as transition element. Clear? But before zinc, that is copper, silver, gold is known as transition element. This series is also known as, that is scandium to copper is known as transition element. Yttrium to silver also known as transition element. Hafnium to gold also known as transition element. What is the basic difference between copper and zinc? So if you consider copper and zinc, copper 229 atomic number, 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 3d10. Zinc 30, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. Actually, copper and zinc both have a same configuration, 3d10, 3d10. Despite of this same number of d electron, copper considered as a transition element, but zinc does not consider as a transition element. Why? Actually, we will consider copper in aqueous medium. In which medium? That is in aqueous medium. In aqueous medium, copper exists as a copper 2+. In copper 2 plus, what happened? One electron lose from 4s orbital and another electron lose from d10. So this one becomes 3d9 configuration. Clear, people? Or if you consider zinc in aqueous medium, this one shows plus 2 stage. So plus 2, that is 4s. This one lose 2 electron from 4s. So this one becomes 3d10. So in aqueous medium also zinc shows 3d10 configuration, but copper shows 3d9 configuration. That's why we consider copper is a transition element, whereas zinc considered as a non-transition element. Clear, people? Okay, so this is the exceptional case. So general, this is the copper is exceptional electronic configuration because 4s2 is unstable, 3d9 is unstable. So if one electron jump from 4s to 3d10, this one is more stable. That's why this one copper shows this kind of confusion. So similar types of electronic confusion also shown by copper, silver and gold. Clear, people? So similar types confusions: chromium, molybdenum and tungsten. So both the group shows exceptional electronic configuration. Clear, people? Chromium, that is chromium, its atomic number is 24, 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 3d5. This one also shows exceptional electronic configuration. Clear, people? Next is atomic radius. If you consider first row transition element and second row transition, first row, second row, third row. First row, say chromium, this one is molybdenum, this one is tungsten. So in first row, say its size is like this, second row its size like this, third row its size. Okay, so what happened? The size between the, this one is gap is large difference, less difference. Clear, people? So first row and second row, the gap between the first row and second row is very large compared to second and third row. Why? Actually in first row only d electron is there, but in second row f electron also introduced. For third row also f electron introduced. So due to the presence of f electron, third row and second row also has a similar size, but first row is very smaller size compared to another two periods. Clear, people? So size difference is maximum, so radius difference also maximum. So atomic size top to bottom, in general atomic size top to bottom increases, here also increases, but not continuously increases. This one is discontinuous increases, that is this one is very small, this one is very large, but this one is similar to size. Clear, people? So their size is similar, so their radius also similar. Clear? Slight difference is there, but not too much compared to first row and second row. Clear? So due to the f electron, that means, why due to the f electron? F orbital shows lanthanoid and actinoid contraction. Clear? F electron shows, due to the f electron shows lanthanoid and actinoid contraction. Why? Because f orbital is a inner transition element. F orbital is a inner orbital. Clear? So due to the inner orbital, interaction force between the nucleus and orbitals are increases. Clear? So due to the increase of effective nuclear charge, their size left to right decreases but not continuously decreases. Clear people? So that's why their size becomes diffuse shape. Clear? This one becomes diffuse shape due to the presence of F electron. So this thing found in Havelock series, this thing found in lanthanide series, this thing found in actinide series. That's why it is also known as lanthanide contraction as well as actinide contraction. So due to the lanthanide and actinide contraction, their size difference also similar. Clear people? Next, atomization enthalpy. What is atomization enthalpy? Atomization enthalpy, if you go left to right, atomization enthalpy also increases. If you go left to right, atomization enthalpy also increases. Atomization enthalpy, this one totally depend on number of unpaired electron. Atomization enthalpy depend on number of unpaired electron. Atomization enthalpy depend on number of unpaired electron. Clear people? Say iron. Clear? Another is chromium. Cr. So this is the chromium block, this is the iron block. Iron, its atomic number is 26. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6. So this d is unfilled, this is not fulfilled. So draw its orbital. 2 3 4 5 पास होता है. How many electron? 1 2 3 4 5, then 6. So how many unpaired is there? That is 4 unpaired. That is n equal to 4, where n is the number of unpaired electron. Clear people? If you draw chromium, its configuration 24, 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 3d5. So this is the unpaired, this is also unfilled. So draw its 1 electron. 1 2 3 4 5 1. Therefore n equal to 6. That is, chromium contains 6 unpaired electron, whereas iron contains only 4 unpaired electron. That is, iron has 4 free hand, but chromium had 6 free hand. So 6 free hand, 1 2 3 4 5 6. So one chromium attached with another chromium by 6 way, but one iron attached with another iron by 4 way. Clear? By 4 hands. Clear? So this bond is lesser tight compared to between the chromium bond. Clear? So this iron, if you try to lose one iron atom from this iron block, so this one require less energy compared to chromium block. So chromium block require more energy because chromium having 6 bond between the chromium atom. So iron having 4 bonds between the iron atom. So that's why this one require less energy if you want to lose one atom from this iron block. So this is known as atomization enthalpy. Metallic, this is the metallic block. So metallic block, that means many number of metals are attached to each other. Clear? So you, if you try to free one metal from this metallic block, that is known as atomization enthalpy. Clear? So atomization enthalpy totally directly depend on number of unpaired electron. So that's why chromium require much more ionization potential compared to iron. Clear people? Due to the presence of mixed number of unpaired electron. So if you consider transition element, that is d block transition elements, chromium, molybdenum and tungsten externally shows higher atomization enthalpy. Clear people? Another example, melting point. Another one is melting point. So atomization enthalpy depend on number of unpaired electron and melting point. Melting point also depend on melting point also depend on number of electron. So chromium, molybdenum, tungsten. So this group 6 contains 6 number of unpaired electrons. So if you consider another d block elements, any element does not having like this or similar number of unpaired electrons. Another elements got lesser number of unpaired electrons compared to chromium, molybdenum and tungsten. Clear people? So that's why chromium, molybdenum and tungsten shows exceptional melting point, exceptionally atomization enthalpy and exceptionally hardness. Clear? So in 3D series, 4D series and 5D series, that is first row, second row and third row. So all of this series, if you compare this block having maximum amount of atomization enthalpy, maximum amount of melting point and maximum amount of hardness. Clear people? So if you compare among themselves, what happened? Chromium to molybdenum, molybdenum to tungsten, melting point increases. MP as well as MP, that is melting point, as well as density, as well as hardness, everything increases. Why? Although all the elements having same number of electrons, but if you consider top to bottom, their size increases. So due to increase of their size, van der Waals attraction force also increases. Clear people? Due to increase of their size, van der Waals attraction force also increases. So one reason is number of unpaired electrons. So all the elements contain same number of unpaired electrons, but bottom element having maximum amount of van der Waals attraction force. Due to the presence of van der Waals attraction force, this metal shows exceptional melting point, exceptional density and exceptional what? Exceptional atomization enthalpy also. Clear people? Next, another things, manganese, technetium, chromium के बाद chromium, molybdenum and tungsten. chromium क्या होता है? Manganese and technetium. So this one is having maximum amount of melting point, maximum amount of atomization enthalpy, maximum amount of hardness also. But if you shift next element, their melting point sharply decreases. Why? This element also contains maximum huge number of unpaired electrons. So what happens if you draw its configuration? Mn25, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d5. This 3d5 configuration is stable configuration. Clear people? This 3d5 configuration is stable configuration. Due to this stable configuration, manganese does not share its valence electron to the another atoms. Clear? So this one does not share, or this one does not try to form bond with another metal. Clear? Because it is a stable configuration. So that's why its interaction force is lesser. So that's why their melting point, density, hardness, everything become lesser. Same reason for technetium also. Another example, zinc, cadmium and mercury. These are soft metal. Then is known as soft metal. Why they are known as soft metal? Actually, if you draw its configuration 30, atomic number is 30, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. Due to the absence of unpaired electron, no interaction force between the zinc metal. Clear? So that's why this one becomes less hard. So this one is softness in nature. But you will consider mercury. This one is liquid in nature at room temperature. What? Liquid. Why? We know top to bottom size increases. Size increases, that means van der Waals attraction force also increases. This one contain stable configuration, that is 4s2 3d10. This one contain 5s2 4d10. This one contain having 6s2 5d10. So all the elements having same configuration. There is no such kind of unpaired, that is there is no unpaired electron. Clear? So why mercury in liquid state, although mercury having maximum amount of van der Waals attraction force? Why mercury shows liquid nature? Actually, first reason, due to the absence of unpaired electron, and second, mercury having maximum amount of lengthened actinide contraction, because mercury having maximum number of f electron. Due to the presence of f electron, there is interaction force decreases. Clear? Due to the lengthened contraction with absence of unpaired electron, mercury goes to the liquid state. Clear, people? Ionization potential. Another topic is ionization potential. Not ionization potential, this one is variable oxygen state. Next one is variable oxygen state. Variable oxidation state. Clear? Say scandium, its atomic number is 21. So draw its configuration 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d1. So this one shows plus 2 oxygen state. This one lose easily, that is scandium shows plus 2 oxygen state. This one lose 3 electron. This is the 18 configuration. This is the most stable. Clear? So this one also shows scandium plus 3 oxygen state. Clear? So between among them, plus 3 is most stable. So scandium shows 2 oxygen state. One is plus 2, another is plus 3. So which one is more stable? Scandium plus 3 oxygen state is more stable. Another is titanium. 18 configuration. Then 4s2, 3d2. So titanium shows first is lose 2 electron, after then this 2, because this 4 presence in the outer orbital. According to above principle, this one comes to the inner side. Why? He was, that is above, scientist above arrange the orbitals according to energy order. So that's why we put 4s before the 3d. Clear? So next what happened? Titanium shows if lose 2 electron, that is titanium shows plus 2. If lose 4 electron, titanium becomes plus 4. But among them which one is more stable? This plus 4 is more stable. So titanium shows 2 types electronic oxygen state, but this one has more stable in plus 4 oxygen state. Another example, manganese. This one is 25, that is 18, 4s2, 3d 5. First manganese lose 2 electron, So this one is plus 2. After that manganese also lose 5 electron, 2 plus 5, that is plus 7. Manganese shows plus 7. So this is the two stable configuration. Clear? So manganese shows oxygen state plus 1 to plus 7, but among them plus 2 and plus 7 is more stable, because manganese lose 7 electron from its outermost shell. This one becomes 18 configuration. According to octet rule, if any elements contain 8 electron of its outermost shell, then that element is highly stable in nature. Clear people? So 18 configuration, that is this one follows inert gas configuration. So if manganese lose 7 electron of its outermost shell, this one get a inert gas configuration. So that's why this is more stable. So manganese, if manganese lose 2 electron, this one get a 3d5 configuration. If manganese lose 7 electron, this one get a 18 configuration. So that's why manganese shows two types of oxygen. One is plus 2, another is plus 7. So among them plus 7 is highest stable in nature. Clear people? So in this way you also find out another oxygen state for another elements. Clear? So this is also given in your books, so all of you see properly. Next one is ionization enthalpy. Next one is ionization enthalpy. Ionization enthalpy. So ionization enthalpy decreases S to D, D to F. Clear? So S block elements require more ionization potential compared to D block elements. D block elements require more ionization potential compared to F block elements. So this one also require stability. This one also depend on the stability of atoms. Clear people? Another this first row, second row and third row. First row, second row and third row. First row, second row, third row, transition element. Transition element. So first row to second row, transition element ionization enthalpy is increases compared to second row to third row. Why? Due to the presence of F electron, due to the increase of F electron. Clear? Top to bottom, number of F electron increase.